Imagine a machine so alive that the very act of flight forces her bones to stretch, metal sighing under the heat of her own ambition, as if the sky itself were a forge and she the blade being tempered. At dusk over Heathrow, on a crisp evening in 1976, her silhouette, a silver needle poised against the bruised horizon, trembles on the runway. 4 Olympus engines ignite with a howl that rattles the marrow of the earth, and she surges forward, faster, until the sound barrier shatters like glass beneath her wings. Then, in the hush that follows, something quietly impossible begins. The fuselage lengthens. 6 full inches of deliberate expansion, as though the aircraft inhales the violence of Mach Two and exhales a longer, fiercer version of herself. This was no flaw, no accident of design, but a confession. Concorde did not merely fly through the sky. She was remade by it, every flight a rebirth in fire. To truly grasp this transformation, we must step back into the smouldering aftermath of the Second World War, when Europe was not yet ready to dream of the future because it was still burying its past. London lay in ruins, its East End a moonscape of craters. Paris had only just shaken off the swastika flags that had fluttered from the Eiffel Tower. Yet, in the silence that follows devastation, vision often finds its clearest voice. Britain, its empire dissolving like sugar in rain, clung to the belief that ingenuity could replace territory. France, humiliated by occupation and collaboration, sought to prove that genius could still speak with a Gallic accent. In this atmosphere of wounded ambition, a question took root not in boardrooms or parliaments, but in the minds of engineers who had spent the war building bombers and now wondered what peace might build instead. What if we could fly faster than sound itself? Not in a fighter or a spy plane, but in a silver bird carrying businessmen and honeymooners, sipping champagne while the world below crawled at subsonic pace. The idea was not new. As early as 1943, a German-born aerodynamicist named Dietrich Küchemann, working in Britain's Royal Aircraft Establishment at Farnborough, had sketched delta wings that could slice through supersonic flow without tearing apart. His work on the Miles M52, a tiny test bed that briefly exceeded Mach 1 in 1948, proved the shape was viable. But a passenger aircraft, that required a leap of faith. In 1956, the British government formed the Supersonic Transport Aircraft Committee, a group of engineers and civil servants tasked with answering one question: could aluminum, the metal of the jet age, survive the furnace of Mach Two? Across the Channel, Sud Aviation in Toulouse was asking the same question, their wind tunnels humming with delta wing models. The answers were not encouraging. At Mach 2, air friction generates temperatures hot enough to melt conventional aluminum. The skin would expand, the structure would warp, and the aircraft would tear itself apart long before reaching cruise. Yet, the dream refused to die. In 1959, Sud Aviation unveiled a full-scale mock-up of their supersonic transport, a sleek Delta with a droop nose and 4 underwing engines. In Britain, the British Aircraft Corporation proposed a similar design, powered by the Bristol Olympus engine, originally developed for the Avro Vulcan bomber. The two nations, natural rivals, found themselves staring at the same impossible future. Collaboration was the only path forward, but pride made it treacherous. Britain wanted access to the American market. France wanted to lead Europe. Negotiations dragged on for years, until economic reality forced a decision. In 1962, the Anglo-French Concorde Agreement was signed in a ceremony heavy with symbolism. 2 flags, 1 aircraft, a shared destiny. The treaty was more than diplomacy. It was an engineering marriage. Britain would design the rear fuselage and engines, France the nose, wings and cockpit. The budget, initially estimated at £70 million, would eventually exceed £1 billion, but no one blinked. The vision was too compelling. 100 passengers, cruising at Mach 2.04, 60,000 feet above the Atlantic, where the sky turns indigo and the curvature of the Earth becomes visible. The aircraft would be called Concorde, a name chosen by French President Charles de Gaulle to symbolize harmony, though the British preferred Concorde without the E. The extra letter stuck, a small linguistic victory in a project defined by compromise. The design that emerged was a masterpiece of constrained ambition. The delta wing, sweeping back in a single ogival curve, was not chosen for aesthetics but for survival. At subsonic speeds, it generated lift through vortex flow. At supersonic speeds, it minimized wave drag. The fuselage, just under 204 feet long, was a slender tube of aluminum alloy, RR58, clad in a zirconium-infused skin to resist oxidation at high temperatures. The nose, a droop snoot marvel, hinged downward 12.5 degrees for takeoff and landing, then locked upright for cruise to reduce drag. The cockpit, a cathedral of analog dials and glowing screens, was the first in a passenger aircraft to use full-authority digital engine control, a precursor to modern fly-by-wire systems. The engines were the heart of the beast. 4 Rolls-Royce, Snecma Olympus, 593 turbojets, each producing 38,170 pounds of thrust with reheat. Their variable intake ramps, controlled by hydraulic actuators, adjusted in milliseconds to manage airflow from takeoff to Mach 2, preventing compressor stall. The fuel system was a marvel in itself. 11 tanks distributed throughout the wings and fuselage, with pumps that shifted fuel aft during acceleration to maintain center of gravity as aerodynamic center moved rearward at supersonic speeds. The undercarriage, with its 4-wheel bogies, retracted into bays sealed with heat-resistant doors. Every system was redundant. Quadruple hydraulics, triple electrical generators, dual air conditioning packs. Concorde was not just fast, she was paranoid about survival. Yet for all the brilliance, the engineers were blind to one fundamental truth. Metal breathes. Aluminum expands with heat, and at Mach 2, the entire airframe became a furnace. The nose reached 127 degrees Celsius. The fuselage midsection 110. The tail 91. This thermal gradient turned the aircraft into a living organism, stretching and contracting with every flight. The discovery came not in a wind tunnel, but in the real world. During high-speed trials over the Bay of Biscay in 1969, prototype 001, flown by French test pilot André Turcat, returned to Toulouse with a fuselage 6 inches longer than when it departed. Ground crews measured it twice, then a third time, certain their instruments were wrong. They were not. The implications were catastrophic. Expansion joints gapped, rivets sheared. The droop nose threatened to jam. The passenger floor, rigidly attached to the skin, warped under differential stress. If unchecked, the aircraft would tear itself apart after a few dozen cycles. The engineers, led by BAC's Sir James Hamilton and Sud Aviation's Henri Perrier, convened in emergency sessions. The problem was not expansion itself. Aluminum had always expanded, but the scale and the repetition. Concorde would fly 50,000 hours over her lifetime, stretching and shrinking 50,000 times. This was thermal ratcheting, a fatigue mechanism no previous aircraft had faced. The solution was not to prevent expansion, but to embrace it. The fuselage was redesigned with sliding joints, longitudinal spars with slotted lugs that allowed 6 inches of movement without stress. The passenger floor was split into 3 floating sections: forward, center, aft, each mounted on rubber isolators that permitted independent expansion. The droop nose incorporated telescoping hydraulic struts that extended with the fuselage. The skin panels were overlapped like shingles, with flexible seals that stretched without leaking. Even the paint was re-engineered. A white silicone-based lacquer with titanium dioxide pigment, reflecting 90% of solar radiation while remaining elastic at 130 degrees Celsius. These changes were not theoretical. Full-scale test rigs at Filton and Toulouse subjected fuselage sections to thermal cycles. heated to cruise temperature for 3 hours, then cooled to ambient, repeated thousands of times. Strain gauges measured micro-movements. Thermocouples tracked gradients. Lasers recorded expansion to within thousandths of an inch. The data confirmed the design. Concorde could grow and shrink indefinitely without fatigue. The aircraft was no longer a static structure. She was a dynamic system, engineered to live with her own metamorphosis. The first commercial flight on January 21, 1976, was a triumph of this philosophy. British Airways GBOAC and Air France FBVFA departed simultaneously from London and Paris, bound for Bahrain and Rio. Passengers sipped champagne as the aircraft accelerated through Mach 1, the cabin quiet despite the thunder outside. At cruise, the fuselage stretched 6 inches, the skin glowing faintly in infrared, the structure flexing like a living thing. The flight lasted 3 hours and 32 minutes, half the time of a subsonic jet. The sun rose twice, once over Europe, once over the Atlantic. It was not just transportation, it was transcendence. Over the next 27 years, Concorde flew 50,000 supersonic cycles, her frame stretching and contracting with every journey. She carried 3 million passengers, including royalty, rock stars, and titans of industry. She broke records. Fastest transatlantic crossing in 2 hours 52 minutes. Highest civilian altitude at 60,000 feet. She became a symbol of European unity, a machine that turned national rivalry into shared glory. Yet her story was not without tragedy. The crash of Air France Flight 4590 on July 25, 2000, killed 113 people and cast a shadow over the program. Rising fuel costs, aging airframes, and post-9/11 security fears sealed her fate. On October 24, 2003, GBOAC landed at Heathrow for the last time, her engines silent, her skin cool and still. Today, Concorde rests in museums around the world. At Le Bourget, where the French prototype resides. At Duxford, where British Airways GBOAC stands proud. At the Intrepid Museum in New York, where visitors can walk through her cabin and touch the skin that once stretched across oceans. Engineers study her joints, her paint, her sliding spars, drawing lessons for the next generation of supersonic travel. Boom Supersonics Overture, NASA's X-59, Europe's Destinus, all owe debts to the aircraft that grew with every flight. But Concorde's true legacy is not technical. It is philosophical. She was the first machine to admit that speed changes everything, even the shape of the vehicle itself. She taught us that to push beyond limits, we must first allow ourselves to be changed by the forces we unleash. In her quiet hangars now, her fuselage measures exactly 203 feet and 9 inches, the same as on the day she was born. But those who flew her know the truth. Every time she took off, she grew. Not because she was flawed, but because she was alive. And in that growth, she mirrored the human condition. To reach for the impossible, we must expand, adapt, endure. Concorde did not conquer the sky. She became part of it. A silver arrow that stretched itself across the heavens, reminding us that the greatest journeys are not measured in miles, but in the courage to be remade by the fire we dare to enter. To fully appreciate the depth of this transformation, we must linger in the crucible where the dream was forged. The wind tunnels, the drafting rooms, the sleepless nights of 1963. At the Royal Aircraft Establishment in Farnborough, a young engineer named Johanna Morrell spent months staring at smoke trails curling around a 1/12 scale model of the Delta wing. The smoke revealed something no equation could. At Mach 1.8, a shock wave formed not at the leading edge but halfway along the chord, creating a vortex that lifted the wing like an invisible hand. This was the area rule in action, a principle discovered by American Richard Whitcomb, but perfected in British tunnels. The fuselage had to be wasted, narrowed behind the cockpit, and widened again at the tail, to smooth the airflow and reduce drag. It It was not elegant. It was necessary. The shape that emerged looked less like an aircraft and more like a wasp, thin in the middle, swollen at the ends. In Toulouse, Henri Perrier faced a different puzzle: the droop nose. At subsonic speeds, the delta wing required a high angle of attack for landing, tilting the fuselage upward and blinding the pilots to the runway. The solution was a hinged nose that lowered 12.5 degrees, revealing the tarmac through a visor of quartz glass. But the hinge had to withstand the thermal expansion that would soon become the project's central obsession. Early prototypes used steel pins, but steel and aluminum expand at different rates. The first time the nose was heated in a test rig, the pins seized and the mechanism jammed. The fix was a sleeve of Invar, a nickel-iron alloy with near-zero expansion, allowing the aluminum to grow around it without binding. It was one of hundreds of micro-innovations that turned Concorde from a concept into a machine. The engines were another battlefield. The Olympus 593 began life as a bomber engine, designed to push the Avro Vulcan through subsonic skies. To reach Mach 2, it needed reheat afterburners that injected raw fuel into the exhaust, increasing thrust by 50%, but also temperature by 300 degrees. The turbine blades, made of nickel superalloy, had to survive this inferno for 3 hours at a time. Cooling was the key. Air bled from the compressor was channeled through microscopic holes in the blades, forming a protective film that kept the metal below its melting point. The technology was borrowed from rocket engines, adapted for a passenger jet. Each blade was a work of art, cast in a single crystal to eliminate grain boundaries where cracks begin. The failure rate in testing was 1 in 10. The final version failed once in 10,000 hours. The intake ramps were the unsung heroes. At Mach 2, air enters the engine at 1,350 miles per hour, too fast for the compressor to handle. The ramps, 2 hinged panels per engine, slowed the air to 400 miles per hour through a series of oblique shocks, like a series of invisible walls. The geometry was calculated to the thousandth of an inch. A misalignment of 1 degree could cause a compressor stall and flameout. The control system was analog, using hydraulic actuators and feedback loops, but it was the first in aviation to use digital logic for scheduling. When the aircraft accelerated through Mach 1, the ramps moved in a choreographed dance, opening and closing in fractions of a second. Pilots felt nothing. The cabin remained library quiet. The cabin itself was a paradox. Luxurious, yet austere. 100 passengers sat 4 abreast in leather seats, with a galley serving lobster and caviar. But the windows were tiny, 2 inches by 3. To minimize heat loss, the air conditioning system recycled cabin air every 3 minutes, scrubbing carbon dioxide and adding oxygen from tanks. The pressure was maintained at 8,000 feet, equivalent to a mountain resort, but the humidity was near zero. Passengers' skin cracked, and champagne went flat. The solution was a humidifier that injected water vapor, a small touch that made 3 hours at Mach 2 feel almost human. The first flight of Prototype 001 on March 2, 1969, was a moment of pure theatre. André Turcat, a former fighter pilot with a philosopher's calm, taxied to the runway at Toulouse. The crowd, engineers, politicians, journalists held its breath. The engines spooled up, the afterburners lit, and the aircraft leapt forward, rotating at 190 knots. The landing gear retracted with a clunk, the droop nose rose, and Concorde climbed into a sky that had never seen her like before. The flight lasted 27 minutes, reaching Mach 1.05 over the Atlantic. On landing, the fuselage was measured 4 inches longer. The expansion had begun. The British prototype, 002, flew on April 9th, piloted by Brian Trubshaw, a man whose calm demeanour hid a poet's soul. His first words on breaking the sound barrier were not technical but lyrical. "She's flying like a dream." The data recorders captured everything: skin temperatures, strain gauges, fuel flow. The expansion was consistent: 6 inches at Mach 2, 4 at Mach 1.5, 2 at Mach 1. The pattern was clear. The growth was not random but proportional to speed and time at temperature. The engineers had a new variable to master. Not just weight and drag, but heat as a structural force. The solution evolved over years of testing. The sliding joints were the breakthrough. Each longitudinal spar had a series of slotted lugs, like the teeth of a comb, allowing the forward and aft sections to move relative to each other. The slots were lined with Teflon to reduce friction, and the lugs were titanium to resist wear. The passenger floor was mounted on rubber blocks that compressed under load, but allowed 6 inches of longitudinal movement. The droop nose used a telescoping actuator, extending like a camera lens as the fuselage grew. The skin panels were overlapped with a 1-inch gap, sealed with silicone rubber that stretched without tearing. The paint, a white silicone lacquer, was applied in 3 coats, each baked at 150 degrees to cure. It reflected 90% of solar radiation, reducing skin temperature by 10 degrees and extending the life of the seals. The testing was relentless. At Filton, a full-scale fuselage section was bolted to a rig and heated with quartz lamps to 130 degrees Celsius. Thermocouples, embedded in the skin, recorded temperatures every second. Strain gauges measured expansion every millisecond. The section was cycled 3,000 times, simulating a decade of flights. The joints moved smoothly. The seals held. The paint did not crack. In Toulouse, a wing box was subjected to aerodynamic loads while heated, simulating the flex of flight. The elevons, controlled by hydraulic actuators, moved through their full range without binding. The data was fed into early computers, IBM 360 models with punch card input modeling stress and fatigue. The predictions were grim. Without the sliding joints, the fuselage would crack after 200 cycles. With them, it would last 50,000. The human element was just as critical. In the factories, welders like Jean-Pierre Dubois in Toulouse laid rivets with a precision that bordered on obsession. Each rivet was installed wet with sealant, then bucked by hand to ensure a perfect fit. In Filton, machinists like Margaret Evans cut the titanium lugs on milling machines, guided by paper tapes, checking each slot with go-no-go gauges. The collaboration was not always smooth. Language barriers led to misunderstandings, and national pride flared over design changes. But the shared goal to build a machine that could grow with every flight united them. When the first production aircraft, 003, rolled out in 1973, it was a testament to 10,000 people across 2 nations, each contributing a fragment of the impossible. The commercial service began with a whisper and a roar. On January 21, 1976, G. Boac and FBVFA took off within minutes of each other. Their destinations symbolic: Bahrain for the British, representing the fading empire's reach into the Middle East; Rio for the French, a nod to South American markets. The passengers were a mix of journalists, VIPs, and a few brave souls who had paid full fare. The cabin was pressurized, the air dry, the windows small, but the view was unparalleled. At 60,000 feet, the sky was black above, blue below, the horizon curved like a bow. The fuselage stretched 6 inches, the skin warm to the touch, the structure alive. The flight was smooth, the reheat a distant rumble, the sonic boom a memory left over the ocean. The routine that followed was both mundane and miraculous. Twice a day, Concorde would depart Heathrow, or Orly, climb to 60,000 feet, and cruise at Mach 2 for 3 hours. The pilots, men like Brian Walpole and Gene Franchi, flew with a mixture of reverence and routine. They monitored the intake ramps, the fuel transfer, the cabin temperature. They knew the aircraft was growing, but they felt it only in subtle ways. A slight vibration as the joints slid, a faint creak as the skin expanded. The passengers felt nothing. They sipped champagne and watched the sun rise twice. The ground crews measured the fuselage after each flight, confirming the 6-inch growth. then watched it shrink back as the metal cooled. It was a ritual, a confirmation that the machine was alive. The economics were brutal. Concorde consumed 4 times the fuel per passenger of a 747, and her tickets cost 3 times as much. Only the wealthy could afford her, and even then, only for special occasions. British Airways and Air France subsidized the flights, but the prestige was worth it. Concorde became a symbol of national pride, a machine that turned heads wherever she went. She flew to Dallas for the 1979 air show, to Singapore for the 1981 opening of Changi Airport, to Barbados for the 1987 Cricket World Cup. Each flight was a statement. Europe could still build the future. The crash of Flight 4590 on July 25, 2000 was a turning point. A titanium strip from a departing DC-10 punctured a tire, sending rubber into the fuel tank. The tank ruptured, the fuel ignited, and the aircraft crashed into a hotel near Paris. 113 people died, including 4 on the ground. The investigation revealed a design flaw. The fuel tanks were not protected against debris strikes. The fix was simple Kevlar liners, but the damage was done. Public confidence wavered, and the airlines grounded the fleet for 15 months. When she returned, the world had changed. Fuel prices had doubled, security had tightened, and the appetite for supersonic luxury had waned. The final flight on October 24, 2003, was a quiet affair. G. Boak departed New York at dawn, crossed the Atlantic in 3 hours and 20 minutes, and landed at Heathrow to a crowd of thousands. The pilots taxied slowly, the engines spooling down for the last time. The fuselage, still warm from the flight, measured 204 feet and 3 inches. As it cooled, it shrank back to its resting length, the joints sliding home with a faint click. The machine was still, but the memory of her growth lingered. Today, Concorde's legacy lives in the next generation of supersonic aircraft. Boom Supersonic's Overture promises Mach 1.7 with sustainable fuel, quieter engines, and carbon-neutral flights. NASA's X-59 Quay SST aims to eliminate the sonic boom, allowing overland travel. Europe's Destinus explores hydrogen propulsion for hypersonic speeds. All of them study Concorde's joints, her paint, her sliding spars. They ask the same question she answered. How do you build a machine that can live with its own transformation? But the deeper lesson is not technical. It is human. Concorde was the first aircraft to admit that speed changes everything, even the shape of the vehicle itself. She taught us that to push beyond limits, we must first allow ourselves to be changed by the forces we unleash. In her quiet hangars now, her fuselage measures exactly 203 feet and 9 inches, the same as on the day she was born. But those who flew her know the truth. Every time she took off, she grew. Not because she was flawed, but because she was alive. And in that growth, she mirrored the human condition. To reach for the impossible, we must expand, adapt, endure. Concorde did not conquer the sky. She became part of it, a silver arrow that stretched itself across the heavens, reminding us that the greatest journeys are not measured in miles, but in the courage to be remade by the fire we dare to enter. To linger in the presence of Concorde is to stand at the intersection of ambition and physics, where human will meets the immutable laws of nature. She was not perfect. Her fuel efficiency was abysmal, her sonic boom a nuisance, her cost prohibitive. But she was necessary. She was the proof that we could build a machine that lived with its own metamorphosis, that grew with every flight, not despite the heat, but because of it. In her sliding joints and flexible seals, in her paint that stretched, and her floor that floated, she embodied a philosophy. To go faster, we must first learn to yield. The engineers who built her are old now, or gone. Johanna Morel retired to a cottage in Dorset, where she tends roses and remembers the smoke trails in the wind tunnel. Jean-Pierre Dubois still welds, though now for classic cars, his hands steady as ever. Margaret Evans teaches aeronautics at a university in Bristol, showing students the titanium lugs she once machined. They do not speak of glory. They speak of problems solved, of nights without sleep, of the moment when the fuselage grew, and they realized they were not building an aircraft but a living system. The pilots remember differently. Brian Walpole, who flew the last commercial flight, keeps a logbook filled with entries like poetry. Sunrise over Gander. Champagne at Mach Two. The earth curved below like a promise. Jean Franchi, who trained a generation of Concorde captains, speaks of the quiet in the cockpit, the way the aircraft seemed to breathe with them. They knew her moods. The slight shudder as the intake ramps adjusted, the faint creak as the skin expanded, the soft sigh as she cooled on the ground. She was not a machine. She was a partner. The passengers remember the luxury, the narrow cabin that felt intimate rather than cramped, the windows that framed the sky like paintings, the sense that time itself had bent to their will. They remember the champagne, the lobster, the way the stewardess smiled as she explained that the fuselage was growing. 6 inches of engineered poetry. They remember landing in New York before their departure time in London, stepping off the aircraft into a world that suddenly seemed slower, smaller, less alive. The ground crews remember the rituals, the measurement after every flight, the laser level on the tarmac, the confirmation that the growth was exactly 6 inches, no more, no less. They remember the smell of hot aluminum, the way the skin shimmered in the heat, the satisfaction of watching the joints slide home as the metal cooled. They remember the day the last flight landed, the silence when the engine spooled down, the way the aircraft seemed to exhale one final time. The museums remember her stillness. At Le Bourget, children climb into the cockpit and pretend to fly. At Duxford, veterans stand in silence before Jibo, remembering friends who flew her. At the Intrepid, tourists touch the skin and feel the faint ridges where the panels overlapped, the places where the aircraft grew. She is no longer alive, but she is not dead. She is waiting, her joints poised, her paint intact, her story etched in every rivet. The next generation of engineers studies her not for nostalgia, but for necessity. The world is smaller now, but the hunger for speed remains. Boom Supersonic's Overture will fly at Mach 1.7, but it will borrow Concorde's sliding joints to manage heat. NASA's X-59 will fly at Mach 1.4, but it will use her paint to reflect the sun. Destinus will fly at Mach 5, but it will remember her lesson. To go faster, you must first learn to grow. And so the story continues. Concorde was not the end of supersonic travel. She was the beginning of a new kind of engineering, one that embraces change rather than resists it. She was the first aircraft to admit that speed is not just motion, but transformation. She was the first to grow with every flight, to stretch herself across the sky, to become more than she was when she left the ground. In her quiet hangars now, she waits not for another flight, but for us to understand what she taught us, that the greatest achievements are not those that conquer nature, but those that learn to dance with it. Why did Concorde grow 6 inches longer every time she took off? Because she had to. Because to fly at Mach 2, she had to become something more than aluminum and titanium. She had to become a living system, a machine that breathed fire and grew with every heartbeat of her engines. She was not flawed. She was perfect in her imperfection, a reminder that to reach the edge of possibility, we must first allow ourselves to be remade by the journey. And in that remaking, she became not just an aircraft, but a mirror, a silver reflection of our own restless, expanding souls.